It's your boy, Professor Rafus, coming at you with some polynomials. Polynomials, they're the general, the quadratic was like ax squared plus bx plus c. Well, what if you had like an x cubed term and an x to the fourth term and an x to the fifth term and so on? I'm going to define polynomials in a bit, but that's what they are. I'll define them in a bit. Easiest way to define them is to look at what they're made out of. So power functions are the building blocks of polynomials. What are power functions? Well, it's easiest to define them by example. It's anything of the form k times x to the p. And that's where p is one of the numbers 0, 1, 2, 3, 4, 5, 6, and so on. So the exponent has to be a positive integer. The coefficient can be anything. K is any real number. Go on. K is any real number. So, for example, I could have 5x to the sixth, or x squared, or 3x, or 2. I honestly feel like I've given this lecture to you before, but I've given this class so many times. If I have, I'll get to new material shortly. So these are all polynomials. No, you know what? We definitely did talk about these already this semester. Or maybe it was last semester. I don't know. I'll just do it again just in case. So like for 5x to the sixth, k equals 5, p equals 6. It's a perfectly good power function. For x squared, well, clearly the exponent is 2, but what's the coefficient? Well, if it's not multiplied by anything, I can always say it's multiplied by 1, because that doesn't change the value. So I could say k equals 1. Here I could say k equals 3, that's easy, but what's the power? Well, x by itself is like x to the first power, because there's only one of them. So I could say p equals 1. Down here, there's no x whatsoever. But I can be real clever and say, well, this is like 2 times 1, and we know that anything to the 0 power is 1. So if we put those two facts together, I could say this is 2x to the 0. And that's how constants technically fit the definition of power functions. So here k is 2 and p equals 0. Because I said right here that 0 was allowed. So these are different kinds of power functions. Only other variation is I could have something like negative 11.47 x to the 903 if I wanted. That would also be a power function. K equals negative 11.47, p is 903. We're not going to deal with power functions that ugly usually, but that's what a power function is. Power functions are the building blocks of polynomials. A polynomial, well, poly means many. And no, I definitely have given this part of the lecture before. Okay, we'll be on new material in a second. This is review. This is review. Because, for example, a polymer is where you have a bunch of plastic molecules agglutinated together. And nomial means term. So this is just many terms added together, and the terms are all power functions. So a polynomial is just a sum of power functions. So for example, I could take my 4 power functions from before and say 5x to the sixth plus x squared plus 3x plus 2 is a polynomial. This one has 4 terms. When it has 3 terms, sometimes we call it a trinomial, and when it has 2 terms, we call it a binomial. 1 term, we could call it a monomial if we wanted for 1 term, monomial. 4 doesn't, let's see, mono, I'm trying to think what language that is. Binomial, trinomial. Are those the Greek roots or the Latin roots? Because I don't know if the next one should be quadra or tetra. I think tetranomial, but no one says that. No one ever says that. Anyway, there's 3 important parts of the polynomial. The highest exponent is the degree. The coefficient on the term with the highest exponent is called the leading coefficient. And this guy right here, the one without any x's on it, is called the constant term. Also, this whole thing is sometimes called the leading term. So the leading term is the term with the degree showing up in it. The degree is the biggest exponent. The leading coefficient is the coefficient on the leading term. And then the constant term doesn't have an x with it. So if I were to write something like 4x squared plus 3x cubed minus 2x, this is that trick polynomial I tried to get you with before. Here the degree is 3, because that's the biggest exponent. I just didn't write it first. If I write it in order like this, we call that standard form. If I don't, then it's not in standard form, but we can still find the degree. And that means this whole thing is the leading term. Then the leading coefficient is this 3. I'll just abbreviate that LC most of the time. And the constant term is 0. It's the same trick as before. I can add 0 without changing the value. So the constant here is 0 because nothing shows up. So we don't say it doesn't exist, we just say it's 0 because technically I could add 0 and not change the value, capiche? So that concludes the reviewy part of this episode. Now I want to do some new stuff. Let's say I have a polynomial like g of x equals, I want to move this closer to me, 2x to the 4th minus 13x cubed plus 2x squared plus 27x minus 18. Sometimes these are called quartics. We name polynomials after their degrees. So a quadratic has a degree of 2, well, not that one, but a quadratic would have a degree of 2, a cubic has a degree of 3 like this guy, and a quartic has a degree of 4 like this guy right here. A quintic would be a degree of 5, and past 5 we don't really say anything. So this is a quartic. Let's say its graph, maybe it looks something like this. It doesn't, but quartics in general, it's kind of like a parabola, but it's got an extra loop. So the most important points on this graph are the roots, however many there are. This polynomial actually has 4 roots, which is why I say this graph is wrong. The most important points are the roots, and then in blue here, the turning points. If your polynomial is degree 2, which is a quadratic, well, then the turning point is just the vertex. If it's not degree 2, then you can't find the turning points without calculus. You have to find the slope and say the turning point shows up wherever the slope is equal to 0. So if you want, you could do a difference quotient, average rate of change from x to x plus h on this monster here, set that equal to 0 and tell me exactly where the turning points are. But I'm not going to ask you to do that because that would be awful and no one wants that. In calculus, you'll learn shortcuts so you don't have to go through that whole computation. But for now, we're just going to say the turning points are a matter of calculus. So as far as our class goes, if it's not a quadratic, the best we can do is find the roots. How are we going to find the roots? So turning points are a matter for calculus. The roots, though, if we can factor, we can use the zero product property. Each factor gives us a root, each root gives us a factor. Roots and factors are 2 sides of the same coin. I'm going to say this like 20 times in the rest of this chapter. 2 sides of the same coin. They correspond. Every root gets you a factor, every factor gets you a root, and it's real easy to go from one to the other. So this mess here, this giant monster, I would need some techniques to try to find out how it factors. I don't have any good factoring techniques for a beast like this. So we're going to learn some new ones in this chapter. We're going to learn called the rational roots theorem. It gives you a short list of possible roots that exist as fractions. Maybe the roots are square roots or complex numbers or some bogus crap like that, but if they're just nice fractions, or if they can be written as a short decimal, well then, this theorem will find them. Like for example, for this polynomial, there's about 20 different rational roots we could have, but no more. So I would go through that list and try different roots until I find out, turns out 1 is a root. One is a root, because if I plug 1 in, all the x parts are just 1. 1 to the 4th is 1, so that'd be 2 minus 13 plus 2 plus 27 minus 18, and that's 0, so 1 is a root. So if 1 is a root, here's what I mean by two sides of the same coin. Saying 1 is a root because g of 1 equals 0 is exactly the same, flipping over the coin, as saying x minus 1 is a factor. Because the zero product property says that if this guy is a factor and the thing is 0, then 1 minus 1 makes 1 a root. To make the whole thing 0, you have to make one of the factors 0. So this is the factor that corresponds to the root 1. Roots and factors always go together just like that. The factor is whatever thing makes your root 0. So now I know what the factor is. I know that g of x is 4th degree, so it should be this thing times a 3rd degree polynomial. Should be this times something cubed plus something squared, da da da. How do I get that? So rational root theorem, that's going to be in 5.5. What we're going to do here, next step of this problem, is something from section 5.4 you'll learn called polynomial division. And what that gets you is you can say g of x divided by x minus 1. And it looks like a long division problem, but it's got a bunch of x's and crap in it. It's honestly not that bad. It's pretty fun once you get used to it. We'll find out that when you divide, you get, turns out, 2x cubed minus 11x squared minus 9x plus 18. It turns out that that's what you get when you divide g of x by x minus 1. So, on the other hand, if I multiply both sides right here by x minus 1, then what this would tell me is that, hold on, what this would tell me is that g of x equals x minus 1 times 2x cubed minus 11x squared minus 9x plus 18. So, as a matter of fact, that's a way that g factors. And now I can focus on factoring this cubic. So I've broken off a linear, and now I've gone from 4 degree to 3 degree. So I'm going to take what's left and keep breaking linear factors off. It turns out x minus 1 goes in again. So we would repeat that process. I could write x minus 1 twice. And then the quotient turns out to be 2x squared minus 9x minus 18. And from there, I can slide and divide. 2 times negative 18 is negative 36. What adds up to negative 9 and multiplies to negative 36? That would be negative 12 and positive 3. So negative 12 and positive 3, except I have to divide by that 2, so it would be negative 6 and 2x plus 3. And I'm going to write the x minus 1s as x minus 1 squared. So g of x is x minus 1 squared times x minus 6 times 2x plus 3. Along the way, we'll also see some other helpful things, like there's something called the upper bound theorem that tells you when you've gone too far to the right to find a root, the lower bound theorem that does the same thing on the left. There's something called the complex zeros theorem that tells you how to find roots that are complex numbers. We're back in chapter 5, so we are going to be talking about complex numbers again. Polynomials can have them. Polynomials are the whole reason we introduced them, so it's time. And there's probably another theorem I'm forgetting. Oh, the remainder and factor theorem. It's really cool. But we'll get to that when we get to division. But yeah, that's the general map of this next part. Is we're going to be learning how to find the roots of polynomials. looking through my notes here. Okay, I see. Okay. I don't actually know where 5.2 ends and 5.3 starts. So I'm going to make this video be a 5.2 and 5.3 video. Like 5.2 is polynomials themselves, and then 5.3 is like the shape of polynomials or something. So let me finish off this example, and then I'll make a video break. I know from x minus 1 that I have a factor. I have a root. A factor of x minus 1 gives me a root of x equals 1. A factor of x minus 6 gives me a root of x equals 6. And a factor of 2x plus 3 gives me a root of negative 3 divided by 2. Because that's what x would make this whole thing 0. So those are the 3 places where this graph will have x-intercepts. And that's why this graph was wrong. I only had 2, but there are 3. Once I know that, probably I can solve whatever story problem I was working on. So again, this chapter is all about different techniques to find these roots. If you want techniques for the turning points, take calculus. I want to say a couple more things about this polynomial, and then I'll break for the next part of the video. Notice it was degree 4. And that means it has to have 4 linear factors, 4 binomial factors. It's got this one twice, and then this one, and then this one. And that always works. The number of factors adds up to the degree of the polynomial. This is a degree 4 polynomial. When I draw a degree 4 polynomial, its graph is kind of interesting. Nah, screw it. I'll do that in the next video. Next video is going to be graphs of polys. Actually, yeah, oh, that'll be 5.3. Tell you what, that's the end of 5.2. Next video will be 5.3. A professional would have pieced this all together off screen, but I am not a professional. So I will see you in a minute. Or like later if you decide, Jesus, you know what I mean.